Good morning. Today we are going to discuss a discrete logarithm and its application chapter. Consider the finite multiplicative group ZP where P is prime. Let G be the generator of the group. That is G raised to 1 mod P, G square mod P, so on to G raised to P minus 1 mod P. We are going to generate the elements of ZP. So I will express this whole thing as y is equal to G raised to x mod P and is referred as modular exponentation with a base G and modulus P. The inverse of this operation is expressed as x is equal to log of x mod P, and this is referred as discrete logarithm. It involves computation of x given the value of p, g and y which belongs to zp. That is, it involves computation of x given p, g and y that belongs to z. For cryptographic applications, the values of P and G are very large. It is somewhere more than hundreds of digits long. However, as seen before, the computation time for performing modular exponentation can be greatly reduced using square and multiply strategy. This is discussed in RSA chapter. The time to compute G raised to x mod P is reduced from polynomial in P to polynomial in log P. Apart from square and multiply technique, the polarized law algorithm and index calculation methods are also used to speed up discrete logarithm problem. Let us consider one simple example. Let P is equal to 131, G is equal to 2 and the discrete log log 2 to 72 mod 131 is equal to 17 because 2 raised to 17 mod 131 gives you 72. Since the values of P and G are very small over here, it is easy to calculate the value of y. But once the value of P and G becomes large, then it is very difficult to get this value. So this one-way property of modular exponent is easy to compute but hard to invert, makes it very useful in cryptographic application. There are numerous applications of discrete logarithm ranging from online secret key encryption and digital signature. We are going to discuss Defi Hellman key exchange in the next topic. Consider two parties A and B that need to agree upon a shared secret key for the duration of current session. One widely used method is Defi Hellman key exchange. So for simplicity, I'll assume that A and B know the generator G and modulus P in advance. This is party A, this is party B. They both know regarding P and G in advance. They then participate in the following sequence of steps to generate a key which will going to be used for that particular current session. So A chooses some random number A, small a. It is a random number whose value is less than p minus 1 and greater than 1. He selects A and he uses it as a partial key. Then he calculates g raised to a mod p and sends it to B. On the other side, B chooses a random integer b. Again, the range of B is same as that of A. That is, P should be less than P minus 1 and it should be greater than 1. And computes the partial key, that is g raised to B mod P and sends it to A. So that means A has computed partial key g raised to A mod P and sends it to B, and B has computed g raised to B mod P and sends it to A. Then on receipt of these two messages, so after A getting a B's message and B getting a A's message, both calculate a session key. The calculation of the session key is as follows. So A calculates g raised to B mod P raised to A, whereas B calculates g raised to A mod P raised to B. And this will lead to a common key, which is g raised to AB mod P, which will going to be used by both the parties for that particular current session. This is how a Defi Hellman technique is used in calculation of secret key. This is a method of exchanging a secret key for that particular session. Now we will going to discuss one example on the same. Let P is equal to 131 and G is equal to 2. Let random number chosen by A is 24. That is, small a is 24. And the partial key calculated by A based on the above explanation, that is g raised to A mod P is equal to 2 raised to 24 mod 131, which is equal to 46. And this 46 A will go to send it to B. Let the random number selected by B is 17. So the partial key calculated by B is g raised to B mod P is equal to 2 raised to 17 mod 131 is equal to 72. These are the partial keys that are calculated by party A and party B. Now, after receiving these partial key, A computes session key. That is equal to G raised to B mod 131 raised to A, that is 17 raised to, what is the value of A? Small a is 24 mod 131. This is equal to 13. And at a receiving side, at B's end, B calculates session key as follows. That is equal to G raised to A mod 131 raised to B. That equal to 46. This value is 46. Already we have calculated it. Raised to 46 mod 131 raised to, the value of B is 17. This in turn lead to 13. The partial keys calculated by A, that is G raised to A mod P, and partial key calculated by B, that is G raised to B mod P, are sent in clear. So even the hacker with the knowledge of partial key and public parameters, that is P and G, it is not possible for him to get the session key, that is G raised to AB mod P, provided the value of P, if it is sufficiently large. In this whole discussion, the random number selected by A and the value that is calculated by A, that is G raised to A mod P, these are the two keys. A is private key of A and G raised to A mod P is public key of A. The possible attack on Defi Hellman key exchange protocol is that it is man-in-middle attack. So in man-in-middle attack, the hacker or the attacker C, who sits between A and B, and he fools both A and B by sending his own keys. To know regarding man-in-middle attack, we'll consider the following scenario, that C is the attacker and B is the party who is supposed to communicate with A. The C is the one who is sitting between A and B and who has a capability to receive or hack the messages of both A and B. Let us see what are the different possibilities that C will utilize to attack both A and B. So, as you know, in Defi Hellman key exchange, to start with, A selects some random number small a, and he calculates a partial key G raised to A mod P and sends it to B. But the attacker does not allow this message to go to a P. What he will do is, after receiving the key from A, the attacker selects his own random number C and he calculates G raised to C mod P and he sends this to B saying that he's A, posing himself as A. And along with this, we'll assume here that both B and C, they know this generator and P. And whenever B gets a message from C thinking that this message is from A, B will respond to that message by selecting its own random number, that is small b, and calculates a partial key, that is g raised to b mod p, and sends it to A. Again, the message that is sent by B will going to be intercepted by C. Moment he gets the message from B, he will going to compute his own message, that is g raised to c mod p, and sends it to A. The C is a random number which is already selected by C. And then after receiving this message, A will go to compute g raised to c into A mod p, which it will go to use it for session, and same is the situation at other side. So here this two will go to calculate session key, that is g raised to c b mod p, and sends it to A. Thinking that sending it to A, both of them, they will in the end going to send it to C. Now G has a session key of both A and B. While communicating with B, he will pose himself as A. While communicating with A, he will pose himself as B. And by doing so, he will going to get the messages of both A and B. And this is how it is possible to crack Defi Hellman protocol. Now we will discuss regarding choice of parameters of Defi Hellman exchange. We have selected modulus P to be a prime and the base G as a generator of ZP. In our example, the P value will go to be at 29. The secret involved in Defi Hellman key exchange includes a private keys A and B. The shared secret key of Defi Hellman exchange is G raised to AB mod P. To minimize the chance of attacker guessing any of these secrets, it is always desirable to they have to be chosen from the large pool of integers as possible. That means my A and B should be very, very large. That means the number of, say, the distinct private keys and the number of distinct public keys, that is AB and A, they are restricted by ZP. So that in case if P is prime, the maximum value of A or AB, what we can select is a P minus 1. And if P is not prime, in that case the value will go to be less than P minus 1. This indicates that to maximize the security, my P value should be very, very large. Again, if the P value is very large, it will go to have an effect on the performance of the algorithm. That indicates that the P value is a trade-off between security and performance. Next, we'll discuss regarding subtle attacks. Next, we're going to discuss regarding the subtle attacks that are happening because of poor choice of P. So, to understand this, we'll consider one example in which my P will going to be equal to 29 and generator of a group, that is G29, is 2. So, consider a party A whose private key, that is a random number that is selected, is A is equal to 7. This is private key of A, and so the corresponding public key is 2 raised to 7 mod 29 is equal to 12. Now we will talk regarding the subgroup of Z29 that is generated by using a generator 12. Now for the subgroup, the G is equal to 12. So this will going to create the elements of the subgroup, that is 12 raised to 7 mod 29, 12 raised to 14 mod 29, 12 raised to 21 mod 29, 12 raised to 28 mod 29, and so on. So this particular generator is capable to generate only 4 elements, that is 12, that is because of 12 raised to 14 mod 29 will going to give us a value 12. Then next G raised to 7 mod 12 raised to 7 mod 29 will going to give us a value 17. Then G raised to the 12 raised to 14 mod 29 will going to generate a value 28, and 12 raised to 28 mod 29 will going to generate a value 1. These are the only 4 elements that will going to be generated by a generator 12. Now regardless whatever may be the value of B's private key, yes, the common secret that is going to be computed will be restricted only to these 4 elements, because the common secret what we will going to calculate will be obtained by multiplying A and B, that is G raised to AB mod 29. So whatever may be the value of B, it will, the final outcome of this will going to be from this set itself. Now because of this, the common secret is one of these 4 elements, so not from 28 elements of Z29. We will express this as B is equal to 4 into I plus J, where J is equal to B mod P, that is B mod 4, because it has only 4 elements. So it is because of that B mod 4. The common secret computed by both A and B will be as it was told over here, that is G raised to AB mod say 29, this equal to G raised to 7 plus 4I, because the 7 is A's value, B value is 4I plus J mod 29. This is my A, this is my B, and then I will simplify this equation, that is 28I plus 7J mod 29, that equal to G raised to 28I plus G raised to 7J mod into mod 29. So this equal to G raised to 28I mod 29 into G raised to 7J mod 29. The property what we have discussed in our say first module, that property I applied over here. Then, but from Fermat's little theorem, that also we have discussed in the first module, we know that this value will going to be equal to 1, because according to the Fermat's theorem, a raised to p minus 1 mod p will be always equal to 1. So that rule we applied over here. So this becomes 1, and the other factor will be g raised to 7j mod 29, and the elements g raised to 7j mod 29 is an element of 12, 28, 17, and so out of these any 4 values will be one which is satisfying this equation. Yes, will go to be the value of j. So we have to select j value such that it should give one of these outcomes. So that will going to be my j. Hence the common secret is restricted to 12, 28, 17 and 1 for any choice of B's private key. So this example exposes the problem that is associated with Defi Hellman's key exchange. So when it selects a poor value of P, this attack is known as small group attack, small subgroup attack. An attacker can eavesdrop on partial secrets exchanged, that is g raised to a mod p and g raised to b mod p. Then he attempts to compute the elements in the sets, that is g raised to a mod p, g raised to 2a mod p, and so on. And similarly he will also attempt to calculate g raised to b mod p, g raised to 2b mod p, and so on. If any one of these sets are smaller, then attacker can very easily guess a common secret key. Using that guesswork, he can launch man in middle attack, which is simpler than the one described in the previous discussion. This type of attack is a passive attack. The attack just now what we have discussed is mainly because that ZP has a small subgroups. By Lagrange's theorem, this could occur if P minus 1 has a small prime factors. For any large prime P, 2 will be always a factor of P minus 1. 2 will be always factor of P minus 1, because P is say odd number. P minus 1 in the end will going to lead to a even number. So naturally 2 will be the one of the factor of P minus 1. However, it is possible to find primes such that rest of the factors of P minus 1 are very large. So it is entirely depends on selection of P. So if a P value is sufficiently large, it is possible, and if it is wisely chosen, then the P minus 1 will lead to a factors 2 and very large numbers such as F1, F2 and so on up to Fk. So these are very large prime numbers. Such a value of phi, so this wise selection of P is referred as Lim-Lee primes. It is referred as Lim-Lee primes. Then by using Lim-Lee prime for a P, we can be sure that only subgroups of Zp are of the size of 2. The subgroups, either it will be of size 2, only 2 elements will be into it, or it will be F1 or F2 or Fk. Yes, they are very large values. A special case of prime is when k is equal to 1. When k is equal to 1, that is p minus 1 has only two prime factors, 2 and very large prime. Only two factors. One is 2, the other one is very large. These are the only two prime factors. So, such p is referred as safe prime. So, it is very safe. So, such p we call it as safe prime. To prevent, in general, to prevent any of these subgroup attacks, so Defi Hellman key exchange software must perform a tests on private keys at both the sides, both on A side as well as B side. If a test fails, the new private key should be chosen. So, thank you. This is regarding Defi Hellman's key exchange. Thank you very much.